Okay, so the goal is to show you a little bit the logical structure of what we're doing right now. And the idea is that, that's an interactive thing, so you really need to give me feedback whether this makes sense for you. And I will start really with the basics again. If you find it too simple, just hold on for 1 second. But if you have questions at any point, let me know. So as you know by now, so let me draw like a little blob here. This is supposed to be the set of all, so it's very informal what I'm saying here. So that's supposed to be the set of all causal fermion systems. Okay? And we want to know what is a minimizer of the causal action principle. So who has an idea how we could do that? You know what a causal fermion system is, so you know, so we fixed those two parameters for now, f and n, and we know this, and you know that I have this thing, and I can, when you give me a causal fermion system, I can calculate this. So how could I find a minimizer of this action principle? What you could do, you could try to do numerics. That's basically where your idea is heading. So you could just say, okay, I think about some very nice algorithm to pick out causal fermion systems here, and I just compare the action. But the problem with that is that the space on which even the measure is defined, remember, that is L of h, right? And if h has dimension f, L of h has dimension f squared for finite dimensional case. And so this is a huge space. So, and remember that if you choose a measure, for example, you could even say I start with counting measures only, right? But remember that those measures you can change the weight. So if you for example, you say, okay, I will start with a counting measure. So let's say I have big L components, and I write it like this. But then I have weights here, which I have to vary as well. And even if you do that, so what you see is I have L squared free parameters. And I did some numerics, so I do some numerics in my PhD. And even if L is 10, we have problems numerically. And you can use all sorts of fancy algorithms, but you have problems. But the point why I'm telling this is, so all of this doesn't really work in the concrete setting. All of those numerical approaches do not work if you really take the causal fermion systems as we have defined it in this lecture, because this space is just too large. Maybe this is important to tell this again to everyone. So if just symbolically, if this is my, let me write rho here, so this is just a symbol. And this is somehow my f as of rho. If I have a function which looks like that, right? So what I want to know is the rho here. But the Euler-Lagrange equations just tell me where this is a local minimizer. In fact, if I only take the first variation, they even tell me only where is a local extremum. So I get all of these. And your idea with a family here, that's like this family, what you do is that's particularly leading to the Euler-Lagrange equation. So what you do is you plug in this family into the action principle, then you take the first derivative and the second one, and then you get equations. That's particularly this. But the essential point, and I hope this is not, correct me if I'm wrong, Felix, but the essential point is, in the concrete setting here, we have some examples where we can do it. You saw examples yesterday in the exercise and today in the exercise. Yesterday and the day before in the exercise. But the point is, when we want this H to have a large dimension, and we know that this is the thing which we have to look at if we want to describe physics, then we have no chance to use any numerical thing. I try to summarize, so what conclusion we had. So first of all, there's the one question, how do you come up with this theory? That's a question we cannot answer right now. You can always ask Felix. The other question is, why do we study it? And I would just say that's because you all signed up to the spring school. So we will study, it's like with a twinkling eye. But that's why we study in exactly this structure. And I would now try to explain to you a little bit more about the logic behind getting out and what you get out and what you put in, if that's okay with you. Okay, so again, this will be very conceptual, so not really precise. So let me just draw a box here. And if you were in my science slam on Monday, you know those are the three nice-looking ladies. So the point is, let's assume those is like the box where we have all physical setups. I just call this informally like that. Okay, so what does this mean? So, or what do I mean by that? That's not universally defined. I just mean, so we have one here, for example, and this one, it's just, let's say we take Minkowski space, and I take just a set of spinors. They do not have to be a solution of the Dirac equation. Just any sort of spinors. That's like one of them. Another one, let me put like little dots on. Another one of them could be, for example, I take, let me denote it by that, I take Schwarzschild space-time and I take a different set of spinors. They could be solutions of the Dirac equation, but they don't have to be, okay? So this is what I do currently in physics. That's of course a huge abstraction. Of course I cannot really go through this list, but I mean that's like the spirit which you would all agree. If I am trying to describe a physical situation, I would somehow take a setup here. Okay, and the essential point is that for every object here, I can reconstruct this as a Causal Fermion system. This goes here. Let me just say this goes here. Okay? So you've seen that yesterday in the morning. I can build a Causal Fermion system out of it. And then also, in a certain sense, I can go back. I mean, you've seen that also yesterday in the morning. When I have a Causal Fermion system, I can introduce those things like the wave function, space-time, causality. And you see in this correspondence, that was the correspondence. So we only made the Minkowski space. We didn't do globally hyperbolic manifolds yet. But in this correspondence, the structures, like I can go back, you know. I take a Causal Fermion system, I introduce wave functions, and this, you saw that's an isometric embedding, for example, of the spin spaces. So I can go back, okay? You can just think about it like this. If this is those physical setups symbol, yeah? If I want to draw it in here, and that's the space of Causal Fermion system, I make it so really tiny, okay? So there's lots of Causal Fermion systems which do not have a correspondence or whatever you call it here. The point is, what we do now is, so we still want to find a minimizer of this causal action principle. And as I said, we do not really know how to do this, so we just do the following. We know there's one local minimizer, one solution of the Euler-Lagrange equation. And this is Minkowski vacuum. So we choose a particular Causal Fermion system in here. Let me make it red. And this is the Minkowski vacuum, okay? So what does this mean? Minkowski vacuum means that we take Minkowski space, and additionally we take solutions now of the vacuum Dirac equation, okay? So we take basically ID / minus m on all the psi I is 0. And we know this is a local minimizer. Remember, local minimizer does not necessarily mean global minimizer. Clear. Okay, so we know this, and we know this is a minimizer. And the fundamental idea is now, so this is Minkowski vacuum. The fundamental idea is, so if we want to find other minimizers, and we know one, so why not just take a look at perturbations of this minimizer, okay? And that's what we do. And what this means in this picture is that from this here, we go in several, I mean, I'll draw them in as directions, so we go in those directions, and we take a look, what happens? I mean, is it still a minimizer? Does the action increase? And the point is like, sorry, the point is, maybe I draw this in. So we have this, like, I do it on the physical side, but of course it corresponds then to variations on this side. Okay? I mean, because I have this, I can, as long as I do something in here, I can always identify it. And now those perturbations, so to speak, they are precisely given by the external potentials. That's the perturbations which we look at. And there's another dimension, so to speak, to this thing. And where I leave, to be precise, this physical setup, that's when I introduce regularizations, okay? So let me just write them in green here. So I have also those R epsilons which I introduce. Even so, if I take an R epsilon, basically I'm not in this abstract physical setup which is currently. And this corresponds to perturbations in here, right? Okay? Okay, and now all I want to do, and nothing more than that I want to know, I would like to know which of those is really the minimizer of the causal action principle, but it turns out if you get down dirty and calculate that, even that is nothing you can do. But what you can do, you can evaluate which of those satisfy the Euler-Lagrange equations. That's what we can do. Okay? So let me just, so that where did I want to draw this?
Right side, right?
On the right side, yeah. Is this, okay. And so I want to study which of those satisfies the Euler-Lagrange equation. And what I find is the following. Okay? I find that only if, so I will, in this tutorial, I will only take a look at where B slash is A slash, yeah? Where B is A slash, that means I only take a look at the vector potential. And the essential point is, here I can perturb with any vector potential which I like. I can, for example, take a vector potential which is defined on Schwarzschild. I mean, that's also R4, but use it here. I can take any, but I find it's only then a solution of the Euler-Lagrange equation if the following holds. So, I mean, perturbation is, or let me write it like that, satisfies the Euler-Lagrange equations only if this equation holds. So that's the Young-Mills equation or the Maxwell equation. So this F, does everybody know what that F is here? Or should I? That's beta, yeah. Okay. So I mean, I find out, and I'm going to explain you now how this works, this logically, this finding this. Say again?
What is that?
F, that's just the field strength. So F alpha beta, let me write it like that maybe, alpha beta, that's just d alpha, a beta minus d beta a alpha. That's what it is. J, good point. J is, so to speak, the current induced by those wave functions which I started with. So J beta is just the sum of all I. And then I have this psi I, gamma beta, psi J. And I just noticed that I, by accident, switched back to the Greek indices. So those are Latin indices, actually. Happens very often to me. Okay, so let me explain you a little bit how this works, how you find this logically. So I said already that we're going to look at a perturbation. So, and let me just write this down. So what that means is I really want now, I take spinos which are solutions of the Dirac equation with external potential, right? And I construct a corresponding causal Fermion system. Did I want to say, and Minkowski space here. And I construct a causal Fermion system. And then I want to know, so I will take something, I will write something down which we will only see tomorrow, but you just have to believe that for a minute. So if I'm on this causal Fermion system side, right, then the equation which we're going to study, which is, so to speak, the Euler-Lagrange equation, it looks in the following way. It's very something, I mean, not very hard. So I take two space-time points, right? And then I have to n, yeah, that's right. And then I have this. What is this now? K again? X and Y. Okay, and we want this equation to be 0. And you know already what this is. The lambda xy, those are the eigenvalues of the operator product x times y. And you know, and this F is just basically are the spectral projectors of the closed chain. So this implies that the closed chain is something like lambda k, f xy, f xy, k. Okay, so why am I writing that down? Because it shows you, so we want to know, I mean, that's coming up with explanations and everything tomorrow, I think, Felix, right? Exactly. Then we want to know when is this equation 0. And what you see, so what we need is, for this causal Fermion system, we're right now on this side, we have constructed the causal Fermion system of the perturbation. So the only thing we really need at that point are the eigenvalues of this operator product. Now we have already seen how can I calculate those eigenvalues, so let me write it like down. The spectrum of x times y. Well, Felix has shown you already on Monday that this is just the spectrum of the closed chain, right? And this is just the closed chain is just the same as p of xy and p of yx. Okay? So what this shows you is that basically the only thing I really need to know to evaluate whether it's a minimizer of this causal action principle is the fermionic projector.
P of xy depends on the measure. If you start with a causal Fermion system and we construct this P of xy, this was this pi x times y, and you evaluate this again on the support of the measure. So this P of xy is kind of equivalent and it's kind of a bit more convenient than working with this measure.
Okay.
Depends on the...
So only this equation should be hold for x and y on the support.
For all x and y on the support, and I mean the way we do it here is that x and y always points in Minkowski space because we kind of identify the support with Minkowski space, and then this should hold like in the usual space-time, this Minkowski space.
And you will also, I mean, in the more general equation, I don't know if we will see them tomorrow, where you evaluate weakly on the light cone, right?
Yeah, in fact, I will also explain.
Yeah.
I mean, the question is still in which sense does this have to be?
Yeah, exactly. So there's a lot of subtleties here, and you will also see that the measure plays a role here. But the essential point is basically we want to check this equation. That's, if this equation is 0, then we know that this is a local extremum of the causal action principle. And now you see, the only thing we need to know to calculate this equation is basically the fermionic projector. And that's what we're doing today. So what do we have to do? So, okay, so don't look at the exercise yet. It's for a minute. It's in a minute. Yeah. Essential point is, I mean, so how do we construct this fermionic projector? You've seen that today. And basically, what we do is we just take the causal perturbation expansion. Okay. So the point is we need to know the fermionic projector of this perturbed situation. So this was the P, I think, how Felix denoted it. And also possibly with perturbations, I didn't write this in there. There are also perturbations like with introducing particles and antiparticles. Okay? And this P, we didn't have there's a non-perturbative construction, but that's just what Felix wrote down today. So that's the formula for, at least this is with PC. So that's just to repeat that get some connection. This is this formula, which gives me the PC for a situation, for example, where I'm here, where I have perturbed with an external potential. And there was this formula, we have this sum over alpha finite, and I have this numerical, this combinatorial factors, and then I have this Cn alpha, and then I have a B, and so forth. Okay? Where those things are always just things like this, those were S, P, or K, if I'm not mistaken. And this was this was just to get the fermionic projector. And why do I need that? Sorry, I repeat myself. I need it in order to be able to evaluate whether the causal Fermion system, which corresponds to a particular perturbation, is a solution of the Euler-Lagrange equations. Okay, but remember that if I only do this, if I only work with this object, then this here is not well-defined. Because this is a distribution. So, I mean, if I write something like this, that's something writing like delta x minus y times delta x minus y, I mean, for physicists. What does it mean? It's not a well-defined object. Or, I mean, question? Exactly, so that's why we introduced the rest. So since we do not know what that's supposed to mean, that's one way of putting it, we introduced the regularization, right? So we had a regularization to make all those things well-defined. So the point is, right now, like this is ill-defined, so we have to introduce a regularization. And I'm coming to that in a minute. And additionally, we see that even if we introduce a regularization, and if we would write it down in a closed form like that, then still the thing is too complicated to really calculate the eigenvalues up there. And that's why we just take a look at perturbation expansion. And we don't expand in X because that's not relativistic invariant, but we expanding psi squared. So we say, okay, why don't we just take a look at those things one order at a time? And that's the light cone expansion. So we introduce the light cone expansion and also have a formula here to get the connection of what Felix has written down there today. Where is it? And this is, so if I now do a light cone expansion, basically what I get is this formula for day. Okay? And I think there's there's no tilde missing. Sorry, okay. So basically this is this formula, which we had at the very end, I think. Psi squared. And then I have one sum. And I have m squared, m to the power of 2n divided by n factorial. And then I have this other term where sum from n to 0, from n to 0 to infinity, to n plus 1, tn, and then I had smooth contributions. Okay, and let me just say again, those t's, they are just for us right now, I mean, those tn's, they were just, if you don't remember precisely, so this tn was just the nth derivative of the t at point A, or m squared is equal to 0. And t was this thing which we wrote down, basically, what Felix wrote down. So t in momentum space, there was just delta of k squared minus m squared, theta of minus k0. Okay? So, yeah. So basically, here, or where here?
So A is m squared.
A is m squared, yeah. That was the shorthand which we used.
And where does the n appear? So nth derivative.
And the nth derivative.
No question. So now we just left out this rec, which I introduced.
Yeah, sorry, I read, yeah. Basically, maybe I should write it down like here.
Such an important point here.
Yeah. But that's not regularization. Yeah. That's.
So what does the rec stand for?
That was what Felix mentioned with the thing with the logarithm, that like if, okay, so maybe we should leave it out, I just say it for the moment. So the problem is if I take a look at this series expansion for the t here, then that was the thing where you see I have this logarithm of m squared. And that's not a light cone expansion. We'll come to that after we have finished this discussion round. We have this exercise for you where you can study a little bit more detailed. What does it mean, a light cone expansion? But just for now, it means like, so if I have a t to the power of n, yeah, this means like it has a divergence. I think, I don't remember exactly, but I think it was 1 over psi squared to the power of n minus 1 probably. Sorry, yeah, no, 1 minus n. Yeah. Okay, so that means.
Positive logarithm, which is not so.
Yeah, okay, so let me just make everything well defined by writing that. So the point is, so in this series expansion, I can say, okay, I want to know what diverges the most. And then I take a look and I see, oh, it's this one, yeah? So the t minus 1 diverges the most. And then in principle, I could say, okay, now I'm just going to take a look at all terms which diverge on the light cone as badly as the t minus 1. And then I calculate this up there. And then I calculate the eigenvalue, and then I check out whether this equation is satisfied. But again, here this formula, we have not yet introduced regularization. Yeah, currently, we have just taken the perturbation expansion, and then we have checked out, okay, so where on the light cone, so how is the divergence of the different term in the light cone? And we need to introduce regularization. And what Felix has shown you at the very end today, that was basically one way of regularizing the fermionic projector. And basically what you saw was that just those terms here, those t's, they just get changed a little bit. So basically regularization just amounts to introducing, like putting a little bit different for the t's here, but the general structure remains. I mean, that was this I epsilon regularization which you saw today. Remember, Felix wrote down what t minus 1 is and t0, and it was not t minus 1 as defined here, but it was changed in this particular case with the I epsilon regularization. It was just changed by taking, instead of t, you read t minus I epsilon. Then you have that. But that's just the very most simplest regularization. And I'm just going to mention that, it's also coming tomorrow. We want to work with the most general, sensible way of regularizing things. And basically what we therefore do is that we do not put in here particular choices, but we just treat those as symbols. And for every regularization which you choose, which makes sense, and for us makes sense means a regularization which does not destroy the tensor scalar structure of the fermionic projector. But that's coming in more detail tomorrow. But for every regularization which you choose, you can just calculate what the symbols are, and then there are calculation rules which tell you if two of those symbols come together, what do you do? I mean, if you multiply two of those symbols, what happens? Those things come up. But that's coming tomorrow. So I just want to say, so let me just put a, so this doesn't make any sense yet, but let me just put it like this to denote that I have now regularized those objects. So you know the meaning of that stuff tomorrow. But now, finally, I'm all set, because now I have regularized. That is, this product over there makes sense, right? Now I can calculate the eigenvalues and can plug it into the Q. And then I can check out for which perturbations. So basically what you do, you study separately the orders on the light cone. So you take a look at the most divergent parts, and you want Q to be 0 for all of the coefficients appearing in front of those. And then you take the next one, and then you do that, and that's how you get out this equation. Then you see really in order for Q to vanish, those equations need to be satisfied. And that is, I think, all I wanted to say to that part. And the first question would be whether Felix wants to add something. And second, I want to give you some time to think about those things.
I would agree that, I mean, that it is, we writing things that's called Causal Fermion Systems. This is just a different language. I mean,
exactly.
You can just, this is still equivalent to the usual formulation in Minkowski space. What changes things is that then one wants to work exclusively with these structures, forget about everything else, and also wants to write down equations in this framework.
And additionally,
these equations and this causal equation is really different. I mean, you can't come up with this starting from Minkowski.
And you do not change around, like it's not equations where the causal action principle, first of all, has no parameter, it's fixed. There's no free parameter. All free parameters come in what I'm going to summarize in a minute, again, what we're currently doing now. And I want to say, like, for me, there's one physical principle, but which makes it like a little bit more plausible, the theory, like that it's really a theory about the universe, and that is, in this theory, there's one object, one structure, which describes both matter and space-time. I mean, we've talked about this before, so probably for you, you think it's so, but it's just for me personally a very nice feature, because, so before Einstein we had time and space, and now we have space-time, and before quantum field theory in the last century, we had three different forces, so I take out gravity, three different forces, nuclear forces, and now we have united them in one theory. And I like it that in this theory, this measure rho is somehow space-time and matter in one thing, but this is a story maybe which we could discuss later, because it's, if you like, because it distracts from the main point. I mean, I'm going to give you an introduction next to the light cone expansion. I prepared that. But currently just, I mean, yeah, maybe let's postpone this question for 1 second, but it's just analyzing how badly things diverge on the light cone. Everything is fine if you're away from the light cone. That's what Felix has shown also. Like if x and y, so let me put it like that, if x minus y squared is not equal to 0, then everything is fine, everything is smooth, like in a small neighborhood of those points. But the point is, if I go to the light cone, things diverge.
I mean, this is like a good explanation, which is like Jan-Hendrik. I mean, there's another intuitive way of understanding why this individual appear on the light cone. And this is like, it has to do with if you think of how the Fourier transform is performed. I mean, in momentum space, the distribution is supported, say, on the mass shell. So this is like this P of K, and then you compute the Fourier transform. And what's the factor is 4 times this P of K to the minus ik minus y. Anyway, what you can do is, I mean, you multiply this, say x minus y is given, multiply this P of k by a plane wave, like here in momentum space, a plane wave, and this x minus y is kind of the frequency of this wave, something like this, and then you integrate on that. So suppose you choose y minus x space-like, so for example y minus x points in this direction. This means that the surfaces of equal phase lie like this. And then you integrate over this, and then it turns out, the phase changes here, and if you integrate it, you have many cancellations, and that drops out, and it turns out that although this integration rate goes all the way to infinity, you get something finite, something which is really smooth. And similarly, this y minus x is time-like, and then you get like strips like this, or the constant phase surfaces lie like this, and again you have cancellations and things, and this is why you get something small and something smooth. Now the situation is different if you say y minus x is light line. Let's look how it looks in this case. In fact, this is not just a qualitative argument, this is in fact how the proof of this whole performance of the continuum works. So that, okay, we have like this P of k like this. Now these surfaces of constant phase, how do they look like? Well, they are now tangent to the light current. So they look kind of like this. And now you integrate over this, and then here again you take the phase change, things cancel, everything is kind of finite. But then there's the contribution over here. This is like what kind of causes trouble when you integrate, because you have all these states here on the mass shell, and they are all in phase. So they come up in this Fourier integral, and they are not multiplied by any phase. So it's the same phase everywhere. And this is what gives rise to the divergence. Exactly. And how the regularization, what does it amount to? You can understand this in momentum space. You have like a scale epsilon in position space. So this is something like 1 over epsilon in momentum space. This is kind of like a regularization scale. And then on this scale, you either just cut off, it's the simplest thing, or you think, well, there's just something different here. There could be different constitutions like this. It doesn't need to be like a slope. There could be something more complicated here. So then you have to say, yes, I don't know really what happens here, but I know that it should all decay on the scale 1 over epsilon. And then in order to, because of this proof code, if you look at this Fourier integral, you make a kind of, well, it's kind of similar to a standard point, because there was the main contribution here in this integral. It's like a large, small expansion, basically like here things hardly change, but in this direction things oscillate faster and faster, and in such a unique case you can analyze them.
But so it's not that you just get those equations, but you get those equations to leading order, and then you have corrections.
Oh, okay.
Yeah. But they're not worked out in a way currently where you could go to an experiment, I would say. Or,
yeah, it's not, yeah. I'll explain this tomorrow, what types of corrections there are. And
yeah.
It's not at a stage where I can say, okay, this should be measured and then you see the difference.
Yeah.